Hi, welcome to Calculus. Today we're looking at some more trig substitutions to try and do more integration. To do these, we're going to be working with right triangles, and we're going to swap out our variable x for an angle, which will allow us to do our integration more easily. So we have three triangles that we have to work with here. And all three, these are right triangles, and they all have the angle theta down here in the corner. So for this one, our variable x is the opposite side, and a constant a is the adjacent side, which if you use the Pythagorean theorem, then makes the hypotenuse a squared plus x squared. Using a little bit of trig then, we can say that x would be equal to a times the tangent of theta, and this square root here of a squared plus x squared is a times the absolute value of secant. It needs to be an absolute value because it's a square root and it's positive. We have another one here. This time my constant is the hypotenuse and my variable is still the opposite side. So in this case, x would be equal to a times the sine of theta, and our square root here at the bottom would be a times the absolute value of cosine of theta. And for our last one, our variable is now the hypotenuse, our constant is one of the legs, it's the adjacent side, and our opposite side is the square root of x squared minus a squared, which gives us x is a secant theta, and the square root of x squared minus a squared is a times the absolute value of tangent of theta. So what we're going to do is we're going to use these triangles, again, to make some substitutions to hopefully make some easier integration. So we have these 5 steps over here to run through. We need to identify the correct triangle. Okay, which one of the 3 is going to make this work for us? We have to write a substitution for x, but then we also have to go ahead and calculate the derivative of x. 3, we're going to substitute back in and simplify the integral. We're going to integrate, and then finally we will reverse the substitution because we don't want an answer with theta in it. We want an answer that has our x in it. So let me get the first example up on the board, and we'll start taking a look at them. All right, so I have 2 examples for us here, and then we'll be done with this section. My first example is the integral of dx over the square root of 9 plus x squared. So in this case, I'm using that first triangle that we had. My a is 3, so I have 3 here, and I have the square root of 9 plus x squared. And using our substitutions, x is 3 tangent theta. Its derivative of tangent is secant squared, so we get 3 secant squared theta d theta. And that square root of 9 plus x squared is 3 absolute value of secant theta. So making those substitutions, you can see I put the dx on top, and the square substitution is on the bottom. And one of those secants goes away, and the 3's, so we're just left with the integral of secant theta d theta. So that gives me the natural log of the absolute value of secant theta plus tangent theta plus c. And then I just have to go back and substitute for secant and tangent. So to do that, if you look over here, the square root was equal to 3 times the absolute value of that secant. So if I just divide both sides by 3, I get a substitution for secant. So my secant turns into the square root of 9 plus x squared over 3. And same thing here with tangent. I want to get rid of tangent, I want it in terms of x. So I divide both sides by 3, and tangent theta becomes x over 3. So that one was pretty nice. This one's a lot messier. I don't think we can actually see the whole thing, so I'll have to move the camera here in just a second. I have the integral of x squared dx all over the square root of 25 minus x squared. So for this one, I'm using the second triangle that we looked at earlier. My a is 5, and so I have 5 for the hypotenuse of the square root of 25 minus x squared for the adjacent side. Doing that then gives me that x is 5 times the sine of theta, and dx would be 5 cosine theta d theta. And then finally, that the square root of 25 minus x squared is 5 cosine theta. Okay, using those substitutions that we looked at right at the beginning of this section. So taking all of that and throwing it into there with one more thing. We do have this x squared. That's not here on my list, except that I can square x. If x is 5 sine theta, x squared is then 25 sine squared theta. So in 25 sine squared theta, that took the place of x squared times 5 cosine theta d theta. There's my dx. All over 5 cosine theta, which took the place of that square root. Cleaning it up, the cosines and the 5's drop out, and I'm left with the integral of 25 sine squared theta d theta. Now, unfortunately, that's a sine squared, which means we have to do a power reduction on it. I pulled the 25 out, And then sine squared is 1 minus cosine 2 theta over 2, but I also pulled that 2 out. So now I just have to integrate this. Integral of 1 is just theta, so I get 25 halves theta. The antiderivative of cosine 2 theta is sine 2 theta over 2, right? Because we have that extra 2 on the inside we have to account for. So taken together with that other 2, I get 25 sine 2 theta all over 4. And I do have a plus c. All right, let's move this computer over so you guys can see the end of the problem. All right, there we go. All right, so we have that 25 over 2 theta minus 25 sine 2 theta over 4 plus c. But we really don't want theta. We want to go back to the x's that we started with. So to do that, the first one's relatively straightforward. We have that way back over here. Let's see, can you see it? We have right about here, and no, you can't see it. X is equal to 5 sine theta. So look back in your notes. There is an x is equal to 5 sine theta at the beginning of this. That was the initial substitution that we did. And so if x is 5 sine theta, dividing both sides by 5, and taking a sine inverse gives us that theta is the sine inverse of x over 5. For the sine 2 theta that we had, we don't have a substitution for that sine 2 theta because all of our trig substitutions just had plain theta in them. So we have to change the angle on the inside. Luckily, there's an identity. Sine of 2 theta is 2 sine theta cosine theta all over 2. So if you're wondering where this 4 came, no, I'm sorry. Sine 2 theta is 2 sine theta cosine theta. I said that wrong. There we go. So that allows me to get down to just regular thetas. 2 and 4 reduce. So I'm left with, yeah. So 2 and 4 reduce, that's where this 2 comes from, and that 25 just comes down. And so then I need to substitute for sine and for cosine. Well, sine we had back over there is, or x is equal to 5 sine theta. So if you just divide both sides by 5, sine is x over 5. And for that cosine of theta, we had that 5 cosine theta is equal to this lovely square root. So again, just divide both sides by 5, and we get that the cosine of theta is the square root of 25 minus x squared over 5. Cleaning it up, the two 5's get rid of the 25, and so we're left with x times the square root of 25 minus x squared over 2 plus c, and all of that is being subtracted from that first part. That's a lot of work. So there you go. There's some fun trig substitutions. Hopefully they go okay for you. Not everything in this section is a trig substitution. So if you need to, look back at there's a table of integrals at the very start of chapter 8. Might come in handy sometimes. So good luck.